I will make it really quick with GANS. Oh yeah, also I need my adapter, I guess. I don't need my adapter. So the purpose of having a GANS section is really to just give a background to people on GANS. If people don't know what generative adversarial networks are, this is just like a very light and easy background for knowing that. It's not really like, okay, let's go into GAN literature and discuss research ideas. So saying that, I'll pull up some slides that I have already committed. And already given a talk about them 6 months ago. But I think because of our short time and because it's a very high-level overview, I think this should be sufficient. Okay. No. Ah, so pretty. I don't know why it's not becoming full screen. Oh, I see, the PDF itself is like that. Yeah. Alright, we'll have to do with it for now. So, generative adversarial networks, I just want to talk a little bit about them. They're a type of neural network formulation that sort of plays this minimax game. So in just this overview is a bit too long. We'll go with the 10 minutes we have, we'll go with whatever we can. So let's start going, let's go one step back. Let's go to unsupervised learning. Typically you're a machine learning crowd, so I'll go easy on these things. I won't go into detail, but typically you have some kind of neural network or something, which is the green box, and then you have inputs, you have outputs, you have some targets, which are the ground truth, and then you train it on some objective. And if you have your targets, it's called supervised learning. And your neural network gets rewards from the outside world. From the loss function that you define, from the targets that the user has. And unsupervised learning is where the model has intrinsic loss functions and intrinsic rewards. That is, no one is, the user is not giving the model any particular targets. The user is only giving it inputs, and the neural network or some kind of machine learning algorithm has to improve itself on some implicit cost function that's part of its internal formulation. And so typically your neural network will have multiple layers. So you might think, why the hell is this thing useful? So you have, if you take a neural network, you'll have multiple layers in your neural network. Let's say those are the blue boxes. Then what you can do is you can have an unsupervised learned neural network and take some parts of that neural network, let's say the first 3 layers, and then add some other new layers, say those yellow boxes, and then train it on some external problem. Let's say you have a lot of input images, and then you do some unsupervised algorithm on a neural network that just tries to improve the generation of these images. And then you want to train it on a task of classifying cats versus dogs. So you take the first 3 layers from this unsupervised network, and then the next 2 layers you initialize them newly, and these will be specialized for the task of classifying cats versus dogs, and be sent to this external cost function that, you'll have a ground truth of what's a cat and what's a dog, and compute the cost function. So that's kind of where unsupervised learning is generally useful. Now, when you come to generative models, so you can have a neural network that's a generator or something that's not a neural network, and then that can produce some distribution that you care about. And in this talk, let's say I'll talk about our input distributions being images. So you can have a generator neural network that maybe takes some inputs or not, but it'll produce some images. So you can have a generative model that's also conditional. For example, you can have the input be some latent variable that controls how much catness or dogness it produces. The input variable, which is typically some noise variable or some structured noise variable, is called a latent variable. And the green box is usually a neural network, at least in the context of this talk. So generative adversarial networks was a paper that was introduced at NIPS 2014. It's a formulation that I'll explain it quickly. So let's say you have some generator, some generative model that takes in some input, like an input noise, and then it generates some sample. Let's say it generates an image. And then you have these generated samples, and then you have your training data, which is like a bunch of natural images. And the cost function is which of them looks more real. So that's the loss function. But typically, to try to come up with a loss function that looks at an image and says, is this real or not, is not it's not obvious how to construct it. You can't really build some trivial mathematical formula that takes in an image and say, okay, is this a real image? Give me some score on whether this is a real image or not. So what we instead would try to do is just learn a loss function, have a neural network be the loss function itself. And that's kind of the formulation of generative adversarial networks, where you have a generator which takes in noise, produces some images, and then you have a discriminator which has to maximize the, given an input image, maximize the probability that it's real or not. But the way you train this is so you can see the discriminator as this learned cost function. And it's trained via gradient descent in a standard way. But the way it's trained is the generator is trying to produce samples that look so real that the discriminator can discriminate them from real samples, like from real images. And the discriminator is trained to take generated images and real images and be classifying them perfectly. That is, it should not be fooled by the generator. So that's why these are called adversarial networks, where the generator is playing an adversarial game against the discriminator, and the discriminator is like trying to not get fooled by the generator. It's this weird minimax problem, which also makes the whole formulation very ill-conditioned. It's very, very hard to train GANs because the formulation is like there's a lot of theory being developed since 2014 on why GANs are hard to train and how to fix them. I won't go into that deep context, but let's just say that people have come with various regularizing tricks on trying to make GAN training more stable using various theories. Like one theory is like the standard regularization theory. Another that we developed was this theory of taking something that was developed in physics called optimal transport theory and trying to apply it to GANs because we saw some very similarities, and we call that formulation Wasserstein GANs. And there's a few other theories, one called boundary equilibrium GANs, which is sort of like SVM formulations where you're like, I want to keep a margin between where my real and fake is. I want to maximize this margin. And so there's a lot of work going on, but the basic formulation, the basic understanding of GANs is this. That is, you have two networks that are like trying to have opposite loss functions. And it's a completely unsupervised formulation. That is, there is no labels that you're giving. You're just giving some input training data, and you're trying to say have like a good generator and have a good discriminator. Now coming back to my unsupervised learning motivation, I'm like, oh, but you can use this in as a pre-trainer to some supervised learning problem. Looking at generally looking at samples, these were the samples generated of natural images in the original GAN paper in 2014. They kind of look crappy, but at that time they were like, oh my god, this is so amazing. We haven't seen such samples in years. And then we published a paper in 2015 that made that it added conditional GANs. So apart from being conditioned on some random Gaussian noise, you can also be conditioned on some class. That doesn't make it unsupervised anymore, but now we've entered into this regime of like how cool of an image can you produce, like kind of just for fun, I guess. And so we these were the images we produced, training a GAN on the Cipher 10 dataset, and for each of the classes, this is a conditional GAN. It takes in which class you want to produce and some noise that controls like the type of the image being produced, and then it produces an image. And then there people have produced video prediction GANs. So these are hybrid GANs where apart from a standard GAN training, you also introduce some kind of mean square error. So you have the loss, which is a combination of a GAN loss and a standard like log likelihood or mean square error based stuff. And one of the things that's a hallmark of GANs is that unlike if you do just pure mean square error based generative models, you would get something blurry. It's like the right top corner or the bottom left corner. You get blurry samples in general, but GANs in general train very, very sharp, produce sharp images, and that's one of the things that people got interested by in GANs. That is, they can produce exact samples from distributions rather than the average of all samples. So we published a paper in late 2015 called DCGAN, which is kind of popular for producing pretty images. It's just a paper on like what kind of neural network structure you should have to make GANs stable and produce like prettier images. And these are the images of bedrooms that DCGAN produced. And we were like, oh, these are really cool bedrooms. And then we also produced faces. And one of the interesting things that these are all generated faces. One of the interesting things that we saw was the latent space of GANs seems to be linear in nature. Like you can try to, so once it's like some simple tricks that we did were similar to what the Word2Vec paper did back in the day a few years ago. We produced images and then we chose the images which were men with glasses and then took their latent variable and then just averaged the latent noise and then produced a new image from the average latent noise, and we got some new generation. Similarly, we took men without glasses, did the same thing, got a generation. Women without glasses did that, and then we took these latent noise and then took the first latent noise, subtracted it from the second one, and then added the third one, and then it produced a generation of women with glasses. And then this is a completely unsupervised generation, right? It doesn't know what men are, what women are, it doesn't know what glasses are, that property was kind of interesting and cool, so we showcased that. So coming back to, okay, how can we use GANs? How can we use them as like unsupervised pre-training algorithms? What we did in the DCGAN paper was we trained a GAN, and then we took the discriminator, removed the last two layers of the discriminator, or the last layer, I can't remember, and then used the first few layers as a feature vector. And then we took some problem which had 700,000 labels or so, And then we reduced the number of labels to 1,000 labels. And we were like, can we do the same problem just with 1,000 labels and get good accuracy with the GAN pre-training? And it turned out we could. So we took the Street View house numbers data set. I don't have a screenshot of that. It's like Google's Street View data set where the car drives through all the cities and takes pictures of the streets, and then you mark the house numbers, and then you want to classify the digits. So it's a 10-way classification problem. There's a bunch of people took 1,000 labels. So the data set is about 700,000 labels large, but then people wanted to try the unsupervised learning regime. So people took the same data set, had 700,000 labels, but then only artificially limited it to having 1,000 labels and a lot of unsupervised training data. In that setting, there's a bunch of methods that were published, and DCGAN with the standard L2 SVM on top as a feature extractor, which is the DCGAN, and some L2 SVM classifier, we got pretty good results. And of course, these results were beaten in subsequent years by a pretty big margin. Another interesting thing that people have been doing, remember how I said GANs are generating very sharp and good images, and that's been something of an interest in the community. So what people did was they took pictures, they removed a middle square of the picture, and they said, okay, generate this middle square. And this is called in-painting. And so for in-painting in general, GANs have been pretty good. So this is some ground truth input without the middle. And a human, if they typically, some artist was asked to draw, they drew that middle picture. On the left is if you use the standard L2 loss based on mean square error loss, and then on the right bottom is if you use some kind of hybrid L2 plus GAN loss, and you see that instead of being very blurry, it's producing sharper generations. I won't go through this because this paper is crappy. We only found out about it later, that it doesn't work in other settings. There's another paper that got published in 2016. They were like, oh, we figured out how to make GANs more stable than they already are. And they just gave like a bunch of tricks, okay, we'll try to smooth the labels instead of asking the generator to train with a hard 1 label for real and 0 label for fake. Can we smooth them out a little bit? And similarly, can we smooth out the labels for discriminator? That kind of helped. They had like a couple of other tricks, but mostly just like a tricks paper. But on the unsupervised setting, there, where is it? In the unsupervised setting with 1,000 labels, the DCGAN got around 22.86%, and that was pretty good. But these guys, with their model, with an ensemble of their 10 models, in a purely unsupervised setting, they had a 5.88% error rate, which is pretty good for 1,000 labels. Back in 2012, I published a paper on the same data set with 700,000 labels, but with neural networks back in the day were on the CPU. And we got 5.1% or something. So with all of our work in 2012 in a fully supervised setting, we could only do 5.1% error rate. And in an unsupervised setting with just 1,000 labels, like GANs were hitting 5.88%. And in subsequent papers of all kinds, this number went down even further. What's next? Well, I gave this talk about a year ago. I was like, well, what are we going to use GANs next? Like, where would they be useful? My personal view is that they would be great to do stuff like forward modeling. And what I mean by forward modeling is having predictors of what's going to happen in the world. So it's something that's very basic intelligence that we have, where if I if I throw a pen at Luca, he's going to, move because he doesn't want to get hit by it. But he already knows before the pen hits him that it's going to come hit him. And these are small predictive models that we as humans have like all the time. And because GANs can produce sharp predictions rather than like the average of all predictions, it feels like they might be a good model to build better predictive models. And that's something that a lot of people are exploring, but people are exploring forward models in general these days, not just with GANs, but in all kinds of settings. That's the end of my talk on GANs. If you want, you could go take a look at how to implement GANs with PyTorch. We have an examples repository. So in this, we have an implementation of DCGAN that produces pretty images. So it's pretty simple. It's only, 267 lines. This, you can see the whole update rule where you're trying to update G by flipping some labels and update D in a different way. So if you have any questions, I'll take them. If not, I think it's already like we're 10 minutes over time. Yeah. No questions, I guess. All right. Great.
No questions?
I think everyone's really tired.
It's been a long afternoon.
Yeah. Thanks a lot for coming. We hope you give PyTorch a try. And feel free to ask any questions on the forums and stuff. I'm always awake. I'm always responding. So.
Yeah, it's a really good community, and we're really encouraged to try it out and be vocal in a nice way, because we're a nice community.
Oh, and if you're an existing user of PyTorch, you want a PyTorch sticker for your laptop, we have some. Feel free to come grab some.
Here's one. I got one too. Thank you, everybody. Bye-bye.